All right, so now we're going to talk about composition methods in the context of variational integrators and discrete Lagrangians. So composition methods for sort of variational integrators. Okay. So the basic question is quite simple. Imagine you have a bunch of one-step methods, and you compose them, maybe possibly at different time steps, and you know the composition of these things, since each of these methods is symplectic, is again symplectic, and so you can ask the natural question whether or not the composition, it's like of those symplectic methods, is again a symplectic method which can be expressed in terms of another generating function, and in particular a discrete Lagrangian. And if so, it's like what that expression is and how is it related to the discrete Lagrangians of the original one-step methods. Okay, so so let's look at a bunch of cases. So I'm going to look at the multiple step case. So let's see. Okay, so let's say that you have you divide each step. So if we divide each step, let's denote this by qk plus 1, right, into s substeps. Okay. And what I mean by that is that you have qk is qk0, and then you have qk1, and then it goes up to qks, for example. And qks is the one which is now what we think of as qk plus 1. Okay? All right. So there's no reason, it's like if you're going to take s substeps, that all these s substeps have to be done using the same discrete Lagrangian. It can be done with different discrete Lagrangians. Okay. Let's call that LDI for each substep. Okay. So and then further imagine that you're taking different time steps for this. So you want to consider the following. So I want to consider the following composition. Composition method. Okay, so I'm going to compose, it's like the discrete Hamiltonian maps. Okay, so I'm going to start with f tilde LD1, right? That's the first of these s possibly different discrete Lagrangians, and I'm going to take a time step gamma 1h. Okay, and I'm going to keep composing this. LD2, and then finally f tilde gamma sh LDS. So this is what I would like to construct, is some sort of composition of all these things with, you know, possibly different time steps for each of these things. All right. So the claim is that this is equivalent to some sort of discrete Lagrangian . Okay. So the claim is that this is equivalent to considering sort of a discrete action sum . To be the following. Let's call that SD. All right, and it depends on qk, which is qk0, all the way up to qks, which is qk plus 1. All right, and this is equal to the sum from k equals 0 to n. I should say that Okay, how should I say this? All right. Okay. And then this goes from k equals 1 to n. Okay, so basically what I'm doing, if you will, is that I'm doing the usual discrete action sum, but then in each of the steps, it's like I add all these multiple sub-steps, if you will. Okay, so I still have the normal sum. Okay, so this should, I guess, go from 0 to let's call it n minus 1. Right, so from k equals 0 to n minus 1. And then the sum from I equals 1 to s of some discrete Lagrangian LDI qk I qk I plus 1 okay, so I goes from 0 to s minus 1. Okay, and then gamma I h. Yes. Okay. All right. So this is what you want to do is you want to consider this discrete action sum, and then you have to write down the stationarity conditions. Right. So with stationarity conditions, which are given by d2 LDI qki minus 1 qki, right, gamma IH plus d1 LD I plus 1 qki qk I plus 1 gamma I plus 1h equals to 0. So this looks very similar, if you will. It's like to discrete all Lagrange equations, and it's derived in a similar way. And you just have to be, again, a little bit careful because now you have a double summation. Both, it's like between, it's like the big steps, and then it's like these little sub-steps, right? Okay, and then, so these are the internal steps, right? These are sort of what joins these sub-steps. It's like relates the sub-steps, and then you have to relate, it's like the qk with the qk plus 1 and so on, all right? And so, so this gives you d2 LDS right, so qk s minus 1 qks gamma sh plus d1 ld 1 qk plus 1 0 qk plus 1 1 and then a gamma 1h, okay, equals to 0. Okay, so this has to do with the fact that if you look at the points qk minus 1, right, qk and qk plus 1, you have these internal stages as well, right? In particular, there's a qk minus 1, s minus 1, and then there's a qk1 here, right, which are immediately adjacent to this. And then the discrete Lagrangian which you use here, right, is LDS. Okay. I should say this is I plus 1. Okay. All right, so there's an LDS here. It's like, and then this one uses the LD1 here. So that's the reason why it's like here you have LDS QKS minus 1, QKS is also QK1, right? So this is equal to both Q qk minus 1s, but it's also equal to qk plus 1, 0. Okay? All right. So, so that's, I'm sorry, that's not what I wanted to say, right? Okay, that's qk1. No, that's qk0. All right, and then this thing here is, no, that's qk1, that's right. Okay, so this thing is both qk minus 1 s as well as qk0. All right, so this thing here is also qk, and this thing here is also qk. All right, and then the thing immediately to the left of this is this qk minus 1 s minus 1 term, and the thing immediately to the right is the qk plus 1 1 term. Yeah, qk. Yeah, all right. So I've mixed up the numbering a bit, but everything should be shifted by 1, I guess. All right. Sorry. All right. Anyway, so hopefully you get the idea. And then these are the internal stage things. It's like where you're just looking at these internal stage points. Okay. So if you had a Runge-Kutta method, then this more or less would be something like the equivalent of your internal stage equations. And then these are the ones which give you the updates at the end. Okay. Okay. So, so that's one way to think about a composition method, is by looking at the discrete action sum for the entire trajectory, and then expressing it as a combination. It's like of the sort of the internal stages, right? So it's almost like a small action sum just for one step itself. And then you can apply Hamilton's sort of the discrete Hamilton's principle to everything, and that gives you these kind of stationarity conditions. All right, so that's one possibility. Okay, and then another possibility, if you will, is to instead of thinking of this as component discrete Lagrangians, you can write the inner sum. It's like as a discrete Lagrangian in its own right, which then only just depends on, say, qk and qk plus 1, and then think of this internal sort of stage equation, which I alluded to, as being part of the definition of some discrete Lagrangian. Okay, so let's see what happens. Okay. Okay, and so this is the whole, so that was the multiple steps point of view. There's also this single step, multiple substages. Okay, multiple substeps, if you will. Okay, so all right, so what you do is that you write down a discrete Lagrangian LD, okay, which depends on qk0 to qks and h, and you define it to be just this sum here, sum from I equals 0 to s minus 1, LD I plus 1, qki, qk I plus 1. There's a gamma I plus 1 here, right? Gamma I plus 1 h. Okay. And then you define the discrete action sum, SD, which depends on, again, everything, right? To be equal to sum from k equals 0 to n minus 1 of LD qk0 to qks h. Okay. and then requiring this is stationary, okay, is equivalent to saying that you want this discrete Lagrangian to be stationary. So so you have di ld qk0 to qks h is equal to 0. All right, and if you expand the definition of LD, it's like in terms of these things, you end up with exactly this condition here, the first condition here. Okay, and then the second condition is the same, or sort of suitably rewritten. So ds plus 1 LD qk0 qks h plus d1 LD qk plus 1 0 to qk plus 1 s h equals to 0. Okay, and then this, of course, if you go back again to the definition of what LD is equivalent to this second one. All right, so yeah, so those two are sort of fairly obviously equivalent. So let's look at a third way of thinking about this. Okay, so you think about it in a single step. So the way you do this is to define a discrete Lagrangian LD, which depends on qk, qk plus 1, and h. And you think of it as being this thing here, right? So the extremum over the internal things. So qk and qk plus 1 are now fixed, right? So qk you should think of as being qk0, and this as being qk s, right? These things are prescribed. It's a little bit, again, like the usual sort of discrete Hamilton's principle, where you fix the endpoints and then you only allow the internal things to vary. So you're applying it more or less now just to you know, the discrete Lagrangian over a small time interval, as opposed to the entire discrete action sum, right? So the extremize over now qk1 to qk s minus 1 of this sum, right? Sum I equals 0 to s minus 1 LD I plus 1 qk I qk I plus 1 gamma I plus 1 h, right? Or you could write it in terms of this sort of multi-point discrete Lagrangian, which is now just LD, but it depends on qk0, qk1, all the way up to qks with a time step h. Okay, so it's all right, and the claim again is that all these things are equivalent. All right, and of course, in particular, it's like when you define this discrete Lagrangian in this way, taking this extremization requires you again to take the stationarity conditions for, you know, it's like LD, it's like for all these internal things, which again, it's like shows that they're equivalent. It's like in the obvious way. All right. So if you construct this discrete Lagrangian in this way, again, more or less, it's like what you do is that you take the appropriate sort of discrete Lagrangians for each of the terms in the composition with the appropriate time steps. You sum it all up, and then it's like all these internal sort of degrees of freedom, which you sort of don't see, right? You extremize over, which is what you do here. Okay, so this is a very simple way, if you will, of constructing the composition discrete Lagrangian, which corresponds to the discrete Lagrangian which generates some given composition method, which is obtained by the composition of you know, a bunch of other discrete Hamiltonian maps, if you will, with prescribed time steps. Okay, so all right, so let me stop here.